What governs the motion of bodies? To move a football at rest, someone must kick it. To throw a stone upwards, one has to give it an upward push. A breeze causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without anyone rowing it. Clearly, some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop motion. You can stop a ball rolling down an inclined plane by applying a force against the direction of its motion. In these examples, the external agency of force like the hands, wind, stream, etc. is in contact with the object. This is not always necessary. A stone released from the top of a building accelerates downward due to the gravitational pull of the Earth. A bar magnet can attract an iron nail from a distance. This shows that external agencies, like gravitational and magnetic forces, can exert force on a body even from a distance. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. The external agency may or may not be in contact with the body. But what if a body is moving uniformly? For example, a skater moving straight with constant speed on a horizontal ice slab. Is an external force required to keep a body in uniform motion? Aristotle's fallacy. The question posed above appears to be simple. However, it took ages to answer it. Indeed, the correct answer to this question, given by Galileo in the 17th century, was the foundation of Newtonian mechanics, which signaled the birth of modern science. The Greek thinker, Aristotle, held the view that if a body is moving, something external is required to keep it moving. According to this view, for example, an arrow shot from a bow keeps flying since the air behind the arrow keeps pushing it. The view was part of an elaborate framework of ideas developed by Aristotle on the motion of bodies in the universe. Most of the Aristotelian ideas on motion are now known to be wrong and need not concern us. For our purpose here, the Aristotelian law of motion may be phrased thus: an external force is required to keep a body in motion. Even a child playing with a simple non-electric toy car on a floor knows intuitively that it needs to constantly drag the string attached to the toy car with some force to keep it going. If it releases the string, it comes to rest. This experience is common to most terrestrial motion. External forces seem to be needed to keep bodies in motion. Left to themselves, all bodies eventually come to rest. The flaw in Aristotle's argument is a moving toy car comes to rest because the external force of friction on the car by the floor opposes its motion. To counter this force, the child has to apply an external force on the car in the direction of motion. When the car is in uniform motion, there is no net external force acting on it. The force by the child cancels the force, friction by the floor. The corollary is, if there were no friction, the child would not be required to apply any force to keep the toy car in uniform motion. The opposing forces, such as friction in solids and viscous forces for fluids, are always present in the natural world. This explains why forces by external agencies are necessary to overcome the frictional forces to keep bodies in uniform motion. Now we understand where Aristotle went wrong. He coded this practical experience in the form of a basic argument. To get at the true law of nature for forces in motion, one has to imagine a world in which uniform motion is possible with no frictional forces opposing it. The law of inertia. Galileo studied motion of objects on an inclined plane. Objects, moving down an inclined plane accelerate, while those, moving up retard. 3. Motion on a horizontal plane is an intermediate situation. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation. That is, it should move with constant velocity. Another experiment by Galileo leading to the same conclusion involves a double inclined plane. A ball released from rest on one of the planes rolls down and climbs up the other. If the planes are smooth, the final height of the ball is nearly the same as the initial height, a little less but never greater. In the ideal situation, when friction is absent, the final height of the ball is the same as its initial height. If the slope of the second plane is decreased and the experiment repeated, the ball will still reach the same height, but in doing so, it will travel a longer distance. In the limiting case, when the slope of the second plane is zero, that is a horizontal, the ball travels an infinite distance. In other words, its motion never ceases. This is, of course, an idealized situation. In practice, the ball does come to a stop after moving a finite distance on the horizontal plane because of the opposing force of friction, which can never be totally eliminated, however. If there were no friction, the ball would continue to move with a constant velocity on the horizontal plane. Galileo, thus, arrived at a new insight on motion that had eluded Aristotle and those who followed him. The state of rest and the state of uniform linear motion, that is, motion with constant velocity, are equivalent. In both cases, there's no net force acting on the body. It is incorrect to assume that a net force is needed to keep a body in uniform motion. To maintain a body in uniform motion, we need to apply an external force to counter the frictional force, so that the two forces sum up to zero net external force. To summarize, if the net external force is zero, a body at rest continues to remain at rest, and a body in motion continues to move with a uniform velocity. This property of the body is called inertia. Inertia means resistance to change. A body does not change its state of rest or uniform motion unless an external force compels it to change that state. Newton's first law of motion, Galileo's simple but revolutionary ideas dethroned Aristotelian mechanics. A new mechanics had to be developed. This task was accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of three laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both implies zero acceleration. The first law of motion can, therefore, be simply expressed as if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is a net external force on the body. Two kinds of situations are encountered in the application of this law in practice. In some examples, we know that the net external force on the object is zero. In that case, we can conclude that the acceleration of the object is zero. For example, a spaceship out in interstellar space, far from all other objects and with all its rockets turned off, has no net external force acting on it. Its acceleration, according to the first law, must be zero. If it is in motion, it must continue to move with a uniform velocity. More often, however, we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, that is, it is either at rest or in uniform linear motion, we can infer from the first law that the net external force on the object must be zero. Gravity is everywhere. For terrestrial phenomena, in particular, every object experiences gravitational force due to the Earth. Also, objects in motion generally experience friction, viscous drag, etc. If then, on Earth, an object is at rest or in uniform linear motion, it is not because there are no forces acting on it, but because the various external forces cancel out, that is, add up to zero net external force. Consider a book at rest on a horizontal surface. It is subject to two external forces: the force due to gravity, that is, its weight W acting downward, and the upward force on the book by the table, the normal force R, which is a self-adjusting force. This is an example of the kind of situation mentioned above. The forces are not quite known fully, but the state of motion is known. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of R equals that of W. A statement often encountered is, since W equals R, forces cancel, and, therefore, the book is at rest. This is incorrect reasoning. The correct statement is, since the book is observed to be at rest, the net external force on it must be zero, according to the first law. This implies that the normal force R must be equal and opposite to the weight W. Consider the motion of a car, starting from rest, picking up speed, and then moving on a smooth, straight road with uniform speed. When the car is stationary, there is no net force acting on it. During pickup, it accelerates. This must happen due to a net external force. Note, it has to be an external force. The acceleration of the car cannot be accounted for by any internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. When the car moves with constant velocity, there is no net external force. The property of inertia contained in the first law is evident in many situations. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backward with a jerk. Why? Our feet are in touch with the floor. If there were no friction, we would remain where we were, while the floor of the bus would simply slip forward under our feet and the back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. If the start is not too sudden, that is, if the acceleration is moderate, the frictional force would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body. It is deformable, i.e., it allows some relative displacement between different parts. What this means is that while our feet go with the bus, the rest of the body remains where it is due to inertia. Relative to the bus, therefore, we are thrown backward. As soon as that happens, however, the muscular forces on the rest of the body come into play to move the body along with the bus. A similar thing happens when the bus suddenly stops. Our feet stop due to the friction, which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. We are thrown forward. The restoring muscular forces again come into play and bring the body to rest. Newton's second law of motion. The first law refers to the simple case when a net external force on a body is zero. The second law of motion refers to the general situation when there is a net external force acting on the body. It relates the net external force to the acceleration of the body. Momentum of a body is defined to be the product of its mass m and velocity v, and is denoted by p equals to m multiplied by v. Momentum is clearly a vector quantity. The following common experiences indicate the importance of this quantity for considering the effect of force on motion. Suppose a lightweight vehicle, say a small car and a heavyweight vehicle, say a loaded truck, are parked on a horizontal road. We all know that a much greater force is needed to push the truck and the car to bring them to the same speed and same time. Similarly, a greater opposing force is needed to stop a heavy body than a light body in the same time, if they are moving with the same speed. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone. The mass of a body is thus an important parameter that determines the effect of force on its motion. Speed is another important parameter to consider. A bullet fired by a gun can easily pierce human tissue before it stops, resulting in casualty. The same bullet fired with moderate speed will not cause much damage. Thus, for a given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and velocity, that is momentum, is evidently a relevant variable of motion. The greater the change in the momentum in a given time, the greater is the force that needs to be applied. A seasoned cricketer catches a cricket ball coming in with great speed far more easily than a novice, who can hurt his hands in the act. One reason is that the cricketer allows a longer time for his hands to stop the ball. As you may have noticed, he draws in the hands backward in the act of catching the ball. The novice, on the other hand, keeps his hands fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly, and this hurts. The conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about. The same change in momentum brought about in a shorter time needs a greater applied force. In short, the greater the rate of change of momentum, the greater is the force. Observations confirm that the product of mass and velocity, that is momentum, is basic to the effect of force on motion. Suppose a fixed force is applied for a certain interval of time on two bodies of different masses, initially at rest. The lighter body picks up a greater speed than the heavier body. However, at the end of the time interval, observations show that each body acquires the same momentum. Thus, the same force for the same time causes the same change in momentum for different bodies. This is a crucial clue to the second law of motion. In the example so far, momentum and change in momentum both have the same direction. But this is not always the case. Suppose a stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed, but its direction changes. A force is needed to cause this change in momentum vector. This force is provided by our hand through the string. Experience suggests that our hand needs to exert a greater force if the stone is rotated at greater speed or in a circle of smaller radius, or both. This corresponds to greater acceleration or equivalently a greater rate of change in momentum vector. This suggests that the greater the rate of change in momentum vector, the greater is the force applied. These qualitative observations lead to the second law of motion expressed by Newton as follows. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Thus, if under the action of a force F for time interval delta t, the velocity of a body of mass m changes from v to v plus delta v, that is, its initial momentum p equaling to mv changes by delta equaling to delta pv. According to the second law, force F equals to a constant k multiplied by delta p divided by delta t, where k is a constant of proportionality. The force F is proportional to the product of mass m and acceleration a. In SI units, force is one that causes an acceleration of 1 meter per second square to a mass of 1 kilogram. This unit is known as Newton. That is, 1 Newton equals to 1 kilogram meter per second square. Let us know at this stage some important points about the second law. 1. In the second law, F equals 0 implies equals 0. The second law is obviously consistent with the first law. 2. The second law of motion is a vector law. If a force is not parallel to the velocity of the body, but makes some angle with it, it changes only the component of velocity along the direction of force. The component of velocity normal to the force remains unchanged. For example, in the motion of a projectile under the vertical gravitational force, the horizontal component of velocity remains unchanged. The second law of motion is applicable to a single-point particle. The force F in the law stands for the net external force on the particle, and A stands for acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body, or even more generally, to a system of particles. In that case, F refers to the total external force on the system, and it refers to the acceleration of the system as a whole. More precisely, A is the acceleration of the center of mass of the system. Any internal forces in the system are not to be included in F. The second law of motion is a local relation, which means that force F at a point in space, location of the particle, at a certain instant of time is related to A at that point at that instant. Acceleration here and now is determined by the force here and now, not by any history of the motion of the particle. Impulse. We sometimes encounter examples where a large force acts for a very short duration, producing a finite change in momentum of the body. For example, when a ball hits a wall and bounces back, the force on the ball by the wall acts for a very short time when the two are in contact. Yet the force is large enough to reverse the momentum of the ball. Often, in these situations, the force and the time duration are difficult to ascertain separately. However, the product of force and time, which is the change in momentum of the body, remains a measurable quantity. This product is called impulse. Impulse equals force times time duration equals change in momentum. A large force acting for a short time to produce a finite change in momentum is called an impulsive force. In the history of science, impulsive forces were put in a conceptually different category from ordinary forces. Newtonian mechanics has no such distinction. Impulsive force is like any other force, except that it is large and acts for a short time. Newton's third law of motion, the second law, relates the external force on a body to its acceleration. The external force on a body always arises due to some other body. Consider a pair of bodies, A and B. Let B give rise to an external force on A. The natural question is, does A in turn give rise to an external force on B? In some examples, the answer seems clear. If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts a force on your hand, and you can feel it. But what if the bodies are not in contact? The earth pulls a stone downwards due to gravity. Does the stone exert a force on the earth? The answer is not obvious, since we hardly see the effect of the stone on the earth. The answer, according to Newton, is yes, the stone does exert an equal and opposite force on the earth. We do not notice it since the earth is very massive and the effect of a small force on its motion is negligible. Thus, according to Newtonian mechanics, force never occurs singly in nature. Force is the mutual interaction between two bodies. Forces always occur in pairs. Further, the mutual forces between two bodies are always equal and opposite. This idea was expressed by Newton in the form of the third law of motion. To every action, there is always an equal and opposite reaction. Newton's wording of the third law is so crisp and beautiful that it has become a part of common language. For the same reason, perhaps, misconceptions about the third law abound. Some important points about the third law, particularly in regard to the usage of the terms action and reaction are 1. The terms action and reaction in the third law mean nothing else but force. Using different terms for the same physical concept can sometimes be confusing. A simple and clear way of stating the third law is as follows. Forces always occur in pairs. Force on a body A by a body B is equal and opposite to the force on the body B by the body. 2. The terms action and reaction in the third law may give a wrong impression that action comes before reaction, i.e. action is the cause and reaction the effect. There is no cause-effect relation implied in the third law. The force on A by B and the force on B by A act at the same instant. By the same reasoning, any one of them may be called action and the other reaction. 3. Action and reaction forces act on different bodies, not on the same body. Consider a pair of bodies A and B. According to the third law, force on A by B equals to the opposite or negative force on B by A. Thus, if we are considering the motion of any one body A or B, only one of the two forces is relevant. It is an error to add up the two forces and claim that the net force is 0. However, if you're considering the system of two bodies as a whole, force on A by B and the force on B by are internal forces of the system A plus B. They add up to give a null force. Internal forces in a body or a system of particles thus cancel away in pairs. This is an important fact that enables the second law to be applicable to a body or a system of particles. Conservation of momentum. The second and third laws of motion lead to an important consequence, which is the law of conservation of momentum. Take an example of a bullet fired from a gun. If the force on the bullet by the gun is F, the force on the gun by the bullet is minus F, according to Newton's third law. The two forces act for a common interval of time, delta t. According to the second law, F delta t is the change in momentum of the bullet and minus F delta t is the change in momentum of the gun. Since initially both are at rest, the change in momentum equals the final momentum for each. Thus, if Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, Pg equals to minus Pb, which means that Pb plus Pg equals 0. That is, the total momentum of the system, which consists of the bullet and the gun, is conserved. Thus, in an isolated system, which means a system with no external force, mutual forces between pairs of particles in the system can cause momentum change in individual particles. But since the mutual forces for each pair are equal and opposite, the momentum changes cancel in pairs, and the total momentum remains unchanged. This fact is known as the law of conservation of momentum, which states that the total momentum of an isolated system of interacting particles is conserved. An important example of the application of the law of conservation of momentum is the collision of two bodies. The total final momentum of the isolated system equals its initial momentum. This is true whether the collision is elastic or inelastic. In elastic collisions, there is a second condition that the total initial kinetic energy of the system equals the total final kinetic energy. Equilibrium of a particle. Equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is 0. According to Newton's first law, this means that the particle is either at rest or in uniform motion. If two forces F1 and F2 act on a particle, equilibrium requires force 1 equals to minus force 2, which means the two forces on the particle must be equal and opposite. Equilibrium under three concurrent forces F1, F2, and F3 requires that the vector sum of the three forces F1 plus F2 plus F3 is equal to 0. In other words, The resultant of any two forces, say F1 and F2, obtained by the parallelogram law of forces, must be equal and opposite to the third force, F3. As seen in Figure 4.7, the three forces in equilibrium can be represented by the sides of a triangle with the vector arrows taken in the same sense. The result can be generalized to any number of forces. A particle is in equilibrium under the action of forces F1, F2, and so on up to Fn, if they can be represented by the sides of a closed n-sided polygon with arrows directed in the same sense. Common forces in mechanics. In mechanics, we encounter several kinds of forces. The gravitational force is, of course, pervasive. Every object on the Earth experiences the force of gravity due to the Earth. Gravity also governs the motion of celestial bodies. The gravitational force can act at a distance without the need of any intervening medium. All the other forces common in mechanics are contact forces. As the name suggests, a contact force on an object arises due to contact with some other object, solid or fluid. When bodies are in contact, like a book resting on a table, a system of rigid bodies connected by rods, hinges, and other types of supports, there are mutual contact forces for each pair of bodies, satisfying the third law. The component of contact force normal to the surfaces in contact is called normal reaction. The component parallel to the surfaces in contact is called friction. Contact forces arise also when solids are in contact with fluids. For example, for a solid immersed in a fluid, there is an upward buoyant force equal to the weight of the fluid displaced. The viscous force, air resistance, etc. are also examples of contact forces. Two other common forces are tension in a string and the force due to spring. When a spring is compressed or extended by an external force, a restoring force is generated. This force is usually proportional to the compression or elongation for small displacements. The spring force F equals to minus kx, where x is the displacement and k is the force constant. The negative sign denotes that the force is opposite to the displacement from the unstretched state. For an inextensible string, the force constant is very high. The restoring force in a string is called tension. It is customary to use a constant tension T throughout the string. This assumption is true for a string of negligible mass. There are four fundamental forces in nature. Of these, only the gravitational and electrical forces are relevant in the context of mechanics. The different contact forces of mechanics mentioned above fundamentally arise from electrical forces. This may seem surprising, since we are talking of uncharged and non-magnetic bodies in mechanics. At the microscopic level, all bodies are made of charged constituents, that is, nuclei and electrons, and the various contact forces arising due to elasticity of bodies, molecular collisions and impacts, etc., can ultimately be traced to the electrical forces between the charged constituents of different bodies. Friction. Consider a body of mass m at rest on a horizontal table. The force of gravity, mg, is cancelled by the normal reaction force N of the table. Suppose a force F is applied horizontally to the body. We know from experience that a small applied force may not be enough to move the body. But if the applied force F were the only external force on the body, it must move with acceleration F by m, however small. Clearly, the body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force, resulting in zero net force on the body. This force, Fs, parallel to the surface of the body in contact with the table, is known as frictional force, or simply friction. The subscript S stands for static friction to distinguish it from kinetic friction. Static friction does not exist by itself. When there is no applied force, there is no static friction. It comes into play the moment there is an applied force. As the applied force F increases, Fs also increases, remaining equal and opposite to the applied force up to a certain limit, keeping the body at rest. Hence, it is called static friction. Static friction opposes impending motion. The term impending motion means motion that would take place but does not actually take place under the applied force if friction were absent. As the applied force exceeds a certain limit, the body begins to move. It is found experimentally that the limiting value of static friction is independent of the area of contact and varies with the normal force, and approximately as mu s in, where mu s is a constant of proportionality depending only on the nature of the surfaces in contact. The constant mu s is called the coefficient of static friction. The law of static friction may thus be written as Fs is less than or equal to mu s in. If the applied force F exceeds Fs max, the body begins to slide on the surface. It is found experimentally that when relative motion has started, the frictional force decreases from the static maximum value. Frictional force that opposes relative motion between surfaces in contact is called kinetic or sliding friction and is denoted by Fk. Kinetic friction, like static friction, is found to be independent of the area of contact. Further, it is nearly independent of the velocity. It satisfies a law similar to that for static friction, Fk equals to mu k multiplied by. The coefficient of kinetic friction mu k depends only on the surfaces in contact. Experiments show that mu k is less than mu s. When relative motion has begun, the acceleration of the body according to the second law is the applied force minus kinetic friction Fk divided by the mass. For a body moving with constant velocity, force equals to the kinetic friction Fk. If the applied force on the body is removed, its acceleration is minus kinetic friction Fk divided by the mass, and it eventually comes to a stop. The laws of friction do not have the status of fundamental laws like those for gravitational, electric, and magnetic forces. They are empirical relations that are only approximately true. Yet they are very useful in practical calculations in mechanics. Thus, when two bodies are in contact, each experiences a contact force by the other. Friction, by definition, is the component of the contact force parallel to the surfaces in contact, which opposes impending or actual relative motion between the two surfaces. Note that it is not motion, but relative motion that the frictional force opposes. Consider a box lying in the compartment of a train that is accelerating. If the box is stationary relative to the train, it is in fact accelerating along with the train. What forces cause the acceleration of the box? Clearly, the only conceivable force in the horizontal direction is the force of friction. If there were no friction, the floor of the train would slip by and the box would remain at its initial position due to inertia and hit the backside of the train. This impending relative motion is opposed by the static friction Fs. Static friction provides the same acceleration to the box as that of the train, keeping it stationary relative to the train. Rolling friction, a body like a ring or a sphere rolling without slipping over a horizontal plane, will suffer no friction, in principle. At every instant, there is just one point of contact between the body and the plane, and this point has no motion relative to the plane. In this ideal situation, kinetic or static friction is zero, and the body should continue to roll with constant velocity. We know in practice this will not happen, and some resistance to motion, that is, rolling friction, does occur. To keep the body rolling, some applied force is needed. For the same weight, rolling friction is much smaller, even by 2 or 3 orders of magnitude, than static or sliding friction. This is the reason why discovery of the wheel has been a major milestone in human history. During rolling, the surfaces in contact get momentarily deformed a little, and this results in a finite area, not a point of the body being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes motion. We often regard friction as something undesirable. In many situations, like in a machine with different moving parts, friction does have a negative role. It opposes relative motion and thereby dissipates power in the form of heat, etc. Lubricants are a way of reducing kinetic friction in a machine. Another way is to use ball bearings between two moving parts of a machine. Since the rolling friction between ball bearings and the surfaces in contact is very small, power dissipation is reduced. A thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. In many practical situations, however, friction is critically needed. Kinetic friction that dissipates power is nevertheless important for quickly stopping relative motion. It is made use of by brakes in machines and automobiles. Similarly, static friction is important in daily life. We are able to walk because of friction. It is impossible for a car to move on a very slippery road. On an ordinary road, the friction between the tires and the road provides the necessary external force to accelerate the car. Circular motion, acceleration of a body moving in a circle of radius, r with uniform speed v, is v squared divided by r, directed towards the center. According to Newton's second law, the force Fc providing this acceleration is equal to mv squared divided by r, where m is the mass of the body. This force directed towards the center is called the centripetal force. For a stone rotated in a circle by a string, the centripetal force is provided by the tension in the string. The centripetal force for motion of a planet around the sun is the gravitational force on the planet due to the sun. For a car taking a circular turn on a horizontal road, the centripetal force is the force of friction. The circular motion of a car on a flat and banked road give interesting application of the laws of motion. Motion of a car on a level road, 3 forces act on the car. 1. The weight of the car, mg. 2. Normal reaction, n. 3. Frictional force, F. As there is no acceleration in the vertical direction, normal reaction, N, is equal to the weight of the car, mg. The centripetal force required for circular motion is along the surface of the road and is provided by the component of the contact force between road and the car tires along the surface. This, by definition, is the frictional force. Note that it is the static friction that provides the centripetal acceleration. Static friction opposes the impending motion of the car moving away from the circle. Static friction F is equal to mu s multiplied by r, the radius of the circle, and g, the acceleration due to gravity. Note that static friction is independent of the mass of the car. This shows that for a given value of s and r, there is a maximum speed of circular motion of the car possible, namely Vmax equals to the square root of mu s or g. Motion of a car on a banked road. We can reduce the contribution of friction to the circular motion of the car if the road is banked. Since there is no acceleration along the vertical direction, the net force along this direction must be 0. The maximum possible speed of a car on a banked road is greater than that on a flat road. At a speed given by v0 equaling to the square root of arg tan theta, the frictional force is not needed at all to provide the necessary centripetal force. Driving at this speed on a banked road will cause little wear and tear of the tires. The same equation also tells us that for speed v less than v0, the frictional force will be up the slope and that a car can be parked only if tan theta is less than or equal to mu s. Solving problems in mechanics. A typical problem in mechanics usually does not merely involve a single body under the action of given forces. More often, we will need to consider an assembly of different bodies exerting forces on each other. Besides, each body in the assembly experiences the force of gravity. When trying to solve a problem of this type, it is useful to remember the fact that we can choose any part of the assembly and apply the laws of motion to that part provided we include all forces on the chosen part due to the remaining parts of the assembly. We may call the chosen part of the assembly as the system and the remaining part of the assembly plus any other agencies of forces as the environment. To handle a typical problem in mechanics systematically, one should use the following steps. 1. Draw a diagram showing schematically the various parts of the assembly of bodies, the links, supports, etc. 2. Choose a convenient part of the assembly as one system. 3. Draw a separate diagram which shows this system and all the forces on the system by the remaining part of the assembly. Include also the forces on the system by other agencies. Do not include the forces on the environment by the system. A diagram of this type is known as a free body diagram. 4. In a free body diagram, include information about forces, their magnitudes and directions that are either given or you're sure of. Example, the direction of tension in a string along its length. The rest should be treated as unknowns to be determined using laws of motion. 5. If necessary, follow the same procedure for another choice of the system. In doing so, employ Newton's third law. That is, if in the free body diagram of A, the force on a due to B is shown as F, then the free body diagram of B, the force on B due to A should be shown as minus F. Action-reaction pairs. Remember that an action-reaction pair consists of mutual forces which are always equal and opposite between two bodies. Two forces on the same body which happen to be equal and opposite can never constitute an action-reaction pair. The force of gravity on the mass and the normal force on the mass by the floor are not action-reaction pairs. These forces happen to be equal and opposite if the mass is at rest. The practice of drawing free body diagrams is of great help in solving problems in mechanics. It allows you to clearly define your system and consider all forces on the system due to objects that are not part of the system itself.